In section 4.3, we're dealing with rate of change and slope. So our two warm-up problems, first one asks us to find the x and y intercepts of 2x minus 5y equals 20, using what we learned in yesterday's or our previous lesson. And number two asks us to describe the correlation shown by the scatter plot, using either positive correlation, negative correlation, or no correlation for your answer. So to check out our answers here, number one, the x-intercept is 10, because remember, in order to find the x-intercepts, we plug in 0 for y, or we just make the y term go away. So we solve 2x equals 20, so x equals 10. For our y-intercept, we plug in 0 for x, or simply make the x term go away, and we solve negative 5y equals 20, which gives us y equals negative 4. So our x-intercept is 10, or the ordered pair 10, 0, and the y-intercept is negative 4, or the ordered pair 0, negative 4. Number two, the correlation shown by this scatter plot is a negative correlation, because as we go from left to right, we are going down. So as x increases, y is decreasing. So that's negative correlation. Our goals for this lesson are to be able to find rates of change and slopes, and to relate a constant rate of change to the slope of a line. So rate of change is a ratio, okay, so a fraction that compares the amount of change in a dependent variable y to the amount of change in an independent variable x. So it's comparing change in y versus change in x. Rise refers to the difference or change in y values of 2 points on a line. Run refers to the difference or change in x values of 2 points on a line. Slope refers to the ratio of rise to run, so rise over run for any points on a line. So here's a nice comparison here. Slope is rise over run, which is equal to change in y over change in x, because rise refers to the difference in y's, run refers to the difference in x's. Okay, and rate of change is generally the same idea, refers more to real-life word problem type situations, but change in dependent variable, which would be y, over change in independent variable, which would be considered x. Okay, so rate of change and slope are often viewed interchangeably. So in this model, it's asking about finding the rate of change over each time period. So from month 2 to 3, from 3 to 5, 5 to 7, and 7 to 8. So because we're finding rate of change, we need to find change in y over change in x. Okay, so let me kind of write that down here. Sometimes I refer to rate of change as ROC equals change in y over change in x. Okay, so you'll see that if we look at these as ordered pairs, so 2, 56, 3, 56, 5, 63, because this is a horizontal XY table, when I'm going from month 2 to 3, if I do my change in y, okay, so from 56 to 56, there's no change, so that change is 0. Over change in x, 2 to 3 was a change or an increase in 1, so 0 over 1 gives us 0, so no change over that time period. So from month 3 to 5 now, we went from 56 to 63 degrees. Well, we know mathematically that 56 plus 7 is 63, so the change in y was 7. And in order to literally do it, you would actually do the second y value minus the first y value. So 63 minus 56 to then give us the correct sign. So 7, positive 7, increase of 7. And then the change in x, if we do the same thing, the second x minus the first x, that's going to be an increase of 2. So 5 minus 3 is 2. So 7 over 2 gives us a change, rate of change of 3.5. Next time period from 5 to 7, okay? So if I find the change in y's, 71 minus 63 is 8, okay? So it increased by 8, the temperature, and the time period was a change in 2 days, 7 minus 5, so 8 over 2 is 4. And then our last one from month 7 to month 8, okay? Change in y's, 72 minus 71 is 1. Over change in x, 8 minus 7 is 1. So if we're asked to then determine which time period we had the greatest the increase at the fastest rate, we would look at simply our rate of change, the simplified answers here, which would be 4, which was from month 5 to 7. Okay, so the key here, rate of change or slope, is change in y over change in x. So let's take a look at that and do that for number 1. It says the table shows the balance of a bank account on different days of the month. Find the rate of change during each time interval. During which time interval did the balance decrease at the greatest rate? So here, my x values would be day number. My y values would be the balance. And because our rate of change is change in y over change in x, we're going to find the differences in y's divided by the differences in x. Now, another way to represent change in, and I think I did show this before, is the Greek letter delta. So delta y over delta x would mean change in y over change in x. Okay, so let's note that. Delta equals change in. All right, so for our first interval here, try to figure out how to show it. So from day 1 to 6, okay, and I look at these ordered pairs. My change in y needs to deal with my y values. So I went from 550 to 285. So when I do my right versus left, so second one minus the first one, 285 minus 550, that gives me negative 265 for my change in y. So yes, we went down $265. And when I divide that by my change in x, well, my change in x, it was an increase in 5 days, literally calculated by 6 minus 1, which gives us 5. So this overall rate of change simplifies to negative 53, because negative 265 divided by 5 is negative 53. Next, to find our rate of change from day 6 to day 16, we're going from here to here. Well, we need to do our change in y over change in x again. So my change in y, I went from 285 to 210. So to find that difference, I need to do 210 minus 285. Which is going to give me negative 75 over my change in x's. I went from day 6 to 16, so 16 minus 6 gives us 10. So that was over a 10-day interval. So negative 75 divided by 10 gives us negative 7.5. Next, I'm going to deal with the time interval from 16 to 22. Okay, so my change in y's balance, I went from 210 to 210. Well, there was no change there, so 210 minus 210 does give me 0. Over my change in x's for that interval from day 16 to 22, that's an increase of 6 days because 22 minus 16 is 6, which gives me a rate of change of 0 divided by 6 is 0. And then for our last interval, from day 22 to day 30, my delta y, my change in y, we went from $210 to $175. So 175 minus 210, that's going to give me negative 35. Over my change in x, well, delta x, we went from day 22 to 30, so 30 minus 22 is 8. And when I simplify 35 divided by 8, or negative 35 divided by 8 technically, that's going to give us negative 4.375. Okay, so we have our different rates of change between each set of ordered pairs. And during which interval did the balance decrease at the greatest rate? Well, that would be interval from day 1 to 6. It decreased at an average rate of $53 a day. Okay, so greatest rate of decrease occurred from days 1 to 5 or 1 to 6. Which is negative 53. Now, if we want to compare these rates of change from one interval to the next, we can do so by plotting these ordered pairs. And that's what we're going to do in the next example. So if we were to approximate, unfortunately that's all we can do based on the x-axis counting by 5s and y-axis counting by 50s, if we approximate each of these ordered pairs, we're going to be able to visually see the different rates of change for each time period. So the ordered pair 1, 550 would be 1-ish, 550 is up here. Then our 6, 285, so 6 is going to be just past the 5, 285 will be a little past halfway between the 250 and the 300, so we're in this ballpark. 16, 210 will be just past the 15 and just past the 200. Then we've got 22, 210, so we're going to be almost halfway between the 20 and the 25 and up at the 210 again. And then 30, 175, so 30 and then 175 will be exactly halfway between the 150 and the 200. So even though we're traditionally not going to draw a series of jagged lines connecting each pair of points, we are in this case just to display these different rates of change. So if I connect the first two ordered pairs, that's a pretty severe slope or rate of change that's negative because we're going down from left to right. It's almost straight down, it looks like. Then connecting my next two ordered pairs, I'm more shallow. Okay, it's not as steep. Then from my day 16 to day 22, we just go straight across. Okay, so nothing had changed during that time period. And then we have another slight decrease here for our last time interval. So if we were to label our rates of change here, which again, this particular graph is not exactly what we're going to be doing in all of Chapter 4. We're just displaying these different rates of change. So the rate of change for our first interval was negative 53. The rate of change for our second interval, I believe, was negative 7, negative 7.5. For our third interval, it was 0. And then for our last interval, it was negative 4.375. Okay, so you can see the difference in steepness when you see this like negative 53 versus the negative 4.375. That line is much more shallow. Okay, that rate of change is much more shallow than the rate of change between our first two ordered pairs. And a rate of change of 0 is just a straight horizontal line. So that's going to be an important piece of information. Okay, so this is going to be what happens a lot in Chapter 4 now, is if all of our connected segments have the same rate of change, then they all have the same steepness and together form a straight line, okay, one straight line. The constant rate of change is a line, the constant rate of change of a line is called the slope of the line. Okay, so slope, as defined earlier, is rise over run, which refers to change in y over change in x. So let's take a look at this first model here. So you can see I've got these ordered pairs that are kind of more definitively labeled on this graph. And the reason they're more definitively labeled is due to the fact that they're what I call perfect points. So they occur right on the crosshairs of our background grid. Okay, so they're perfect points. They're not just kind of in the middle of a block somewhere. And what we do is we need to go from one perfect point to the next. I usually go left to right because that's how we generally read. And because slope is rise over run, I'm going to do my rise first. So I'm going to go either up or down first until I'm even with the next perfect point. And then I'm going to run, so go left or right until I'm actually on the next point. Okay, and I'm going to calculate, I'm going to count how many boxes I rise and how many boxes I run. And I'm going to write then the slope as a fraction of rise over run. Crazy stuff going on over here. I'm not sure what this is. All right, so if I look at my first perfect point down here, okay, and I say, okay, I want to go to this point, but we can only travel north, south, east, and west. I can only travel straight along the city streets. I can't walk through blocks or walk through buildings or jaywalk, okay? So to go from this perfect point to the next perfect point, if I rise first, I'm going up 1 unit, 2 units, 3 units. So the rise is 3. I then turn the corner and run to the right, 1 unit, 2 units. So run of 2. So rise is 3, run is 2. Notice from this point now to the next perfect point, rise, go up 1, 2, 3 units, rise of 3. Go to the right, run 1, 2 units till I'm at my next point, and rise of 3, run of 2 to our last point. So rise is 3, run is 2, which makes our overall slope 3 over 2. Okay, so on this model, Notice there are 2 perfect points that are in fact marked. Okay, so I always go left to right because to me that makes the most sense. Okay, so if I go from my left point to my right point, okay, in order to get even with it by going up and down first, I need to go down 1, 2, 3 blocks. And because we went down 3 blocks, the rise is -3. Okay, now we stand on the corner, we turn the corner, and now we travel to the right until we get to that next point. So now I need to travel 1, 2, 3, 4, 5, 6, 7, 8, 9 blocks to the right. So that's a run of +9 because going to the right would be seen as positive. So when I put my rise of -3 over my run of +9, I can then simplify it. 3 over 9 is 1/3 and it's a negative. Okay, so the slope, simplified slope, is -1/3. So let's look at example 3. I need to first find myself 2 perfect points that I'm going to travel between. Okay, so as I kind of go along my line, right here at -5, -1 is a perfect point. Okay, it occurs right on the grid lines. As I continue traveling, my y-intercept is a perfect point, right on the grid lines, or the crosshairs, whatever you want to call it. Okay, so now I'm going to do my rise and my run. So going from my left point to my right point, I'm first going to do my vertical, my rise. Okay, and because I need to go down, it's just going to be negative. So I need to go down 1 block, 2 blocks. Okay, so let me make this as a line here. So I'm going to go down 2 blocks and just chill there at the corner. So our rise is -2 because we had to go down 2 units. And we were just hanging on the corner waiting for the light to turn green. Okay, now we're going to turn right and we're going to travel to the right and run 1, 2, 3, 4, 5 units. So we have now run 5 units to the right. And again, to the right would be seen as positive. So our run is 4. So when I'm talking about my slope being equivalent to rise over run, my rise is -2 over, and I think my run was actually 5, wasn't it? Sometimes I say things and write things that are completely different. Run was 1, 2, 3, 4, 5. Yeah, sorry. The run was +5. Run of +5. And I can't simplify -2 over 5. So that means my answer here for my slope, it's just -2/5. And we like slopes to be in fraction form. If we look at number 4, we do have perfect points already plotted for us. Okay, so we've got 2 perfect points, and you might be looking at this like, we're rising, but we're not running. Well, that's very true. So if we say rise over run, let's start from the bottom point. If I rise to get even with the next point, I've got 1, 2, 3, 4, 5, 6 blocks that I rose over. I didn't need to run anywhere. I didn't go left or right at all, right? Now, if I do 6 divided by 0 in my calculator, I'm going to get an error message, okay, because you cannot divide by 0 ever, ever, ever. So this slope is what we call undefined. Okay, the slope of all vertical lines Not sure what's happening here with my pen here. The slope of all vertical lines is undefined. Okay, so any vertical line will have an undefined slope. Think about it as like a vertical wall. We can't walk up a wall, it's impossible. Okay, so slope is undefined. Now the next one, you might be thinking, well, we're running, but we're not rising. Well, let's write our rise over run. And this particular problem is a good one for two reasons. A, we don't have to rise. Okay, so the rise is 0. Now my run, what we have to be careful with is each of these grid lines in the background, it's not 1 unit, right? Because if this is 0 and that's -4, that means on the x-axis, each of these tick marks is 2 units, okay? 0, -2, -4, -6, -8. So when we run from our left point to our right point, every box counts as 2. So 2, 4, 6, 8, 10, 12. So our run is +12. Well, 0 divided by 12 we can do. We can have 0 on the top, and that's going to give us 0. Okay, so all horizontal, this is a horizontal line. All horizontal lines will have a slope of 0, as we actually displayed up here in our second example. Okay, when that rate of change was 0, it was a horizontal line. All right, now using 4 and 5 for number 6 and 7, 6 we have a vertical line. So this slope is undefined. Okay, we're rising, but we're not running at all. So we're rising a number, running 0. Anything divided by 0 is undefined, can't walk up a wall. And in number 7, we have a horizontal line. It's a piece of cake, it requires no effort, well, little. It requires next to no effort to walk across a flat horizontal floor. So this slope of all horizontal lines is 0, or number 7. Okay, so in number 3, we had a negative slope. Just like negative correlation, the line went down from left to right. Up here, in this image here, this slope was positive. It was a +3/2. Well, going left to right, the line went up. So we have a negative slope, we have a positive slope, we have a slope of 0, horizontal line, and undefined slope for a vertical line. So that brings us to this point right here. We can have positive slopes, a line that rises from left to right, negative slope, a line that falls from left to right. Slope of 0 is a horizontal line, and an undefined slope is any vertical line. All right, so we've got a couple problems here, 8, 9, 10, and 11, that are just simply asking whether the slope is positive, negative, 0, or undefined. Okay, so you can use the piece of information just above in order to help you. But I would like you to simply identify whether the slopes are positive, negative, 0, or undefined of these 4 graphs. Hopefully you got positive, negative, undefined, and positive. Okay, so 10 was undefined because it's a vertical line. Okay, we do then have a little infographic down here talking about the comparison of slopes. The larger the absolute value of the number, the more severe or steep the line will be, whether it's positive or negative. I do want to find the actual slope of number 8 by calculating rise and run, because it is good practice. So I'm going to find 2 perfect points and walk those city blocks. So I'm going to pick this one right here. And, well, there's another perfect point right next to it. Boop. Okay, so if I do my rise first and then my run and I go left to right, my rise is going to be, well, let's make sure that each tick mark is 1 unit. On the X, 1, 2, 3, 4, good. On the Y, -1, -2, good. Okay, so on the rise, we go up 1. So our rise is +1 over our run. Pen is acting funky today. Over the run, once we go up and then turn the corner, we run to the right 1 unit. And because it was to the right, that's also a positive. So we had to go up 1, right 1 to go from the left perfect point to the right perfect point, which I defined. And 1 over 1 gives me a slope of 1. Okay, so we'll get a lot more practice with these problems, but I just wanted to do an extra one.